Imagine you're baking a cake. Some steps are quick, like adding a teaspoon of salt. Others take more time, like mixing the batter. In computer science, we call this time complexity. It's how much longer a program takes as the input grows. Why does this matter? Well, a slow program is like a slow oven. It takes forever to get the job done. When we write code, we want it to be fast and efficient, especially when dealing with lots of data. That's where understanding time complexity comes in handy. By analyzing how long our code takes to run with different amounts of data, we can make smarter choices about which algorithms to use. This helps us write programs that are faster, smoother, and more scalable. So let's dive in and explore the fascinating world of time complexity. To talk about time complexity, we use something called Big O notation. Don't let the fancy name scare you. It's just a shorthand way to describe how the runtime of our code grows with the input size. Let's say you have a list of names and you want to find your friend's name. If you check each name one by one, that's called linear time, and we write it as O on. The N represents the number of names in the list. Big O notation focuses on the most important part of the runtime, how it changes as the input grows. We ignore constant factors, so O to N is the same as ONN. It's all about the big picture. Not all algorithms are created equal when it comes to time complexity. Some are lightning fast, while others crawl along at a snail's pace. Let's compare some common time complexities. O1. Constant time. This is the holy grail of efficiency. No matter how big the input, the runtime stays the same. Think of looking up a specific word in a dictionary using its index, or ON, linear time. The runtime increases proportionally to the input size. Imagine searching for a specific house number on a street. You might have to check each house one by one, ON squared. Quadratic time. The runtime squares with the input size. This can get slow quickly. An example is comparing every item in a list to every other item. Understanding these different complexities helps us choose the right tool for the job. If we're dealing with massive data sets, we'll want to avoid algorithms with quadratic or worse time complexity. Time complexity isn't just an abstract computer science concept. We encounter it all the time in everyday life. Cooking, making a sandwich for one person is quick, O1. But cooking for a large family gathering takes longer, ON. Searching, finding a book in a sorted library using the Dewey Decimal System is fast, O log n. But searching through an unsorted pile of books could take forever, ON. Traveling, driving to the grocery store down the street is quick, O1. But driving across the country takes much longer, ON. By understanding time complexity, we can make smarter choices about how we approach problems, both in code and in life. It's all about finding the most efficient way to get things done.